Let's now look at derivative equals some function of y, those sorts of differential equations. We can easily separate these. So we can easily end up with integral of dx is equal to integral of dy over that function of y. So that's not an issue. Because really what we've got there is a first order linear differential equation. If I was to rearrange it, I could write it like that. It just happens that function x is equal to 0. That's all. Let's look at this one. Y dx is equal to some constant y minus n, and we've been given an initial condition that y0 is n plus a. Separate out our variables, and I'll do it as a definite integral. We've been told when x equals 0, y is n plus 8. We're looking for that link between y and x. Left hand side we get a log function. The right hand side, well, it's just x. Okay. Substitute into the log, I get log of y minus n over a, but we want to make y the subject, so we exponentialize, if that is a word. E to the power of kx is the absolute value of y minus n over a. Therefore y minus n is equal to some constant times e to the kx, y is n plus a e to the kx. There's our solution. Now you might actually recognise that solution because in fact it's what we looked at previously with our growth and decay. It's our modified growth and decay formula. Let's look at this one. dy dx is e to the power of 2y minus 1. Again, let's separate it out. Now on the left hand side we have an exponential we're integrating. So we get minus a half e to the 1 minus 2y is x plus a constant. Of course I have to get rid of the exponential, so log both sides. Alright, multiply everything by -2, log both sides, and then divide by 2, we get, there it is, half of 1 minus the log, c minus 2x. Square root of 1 minus y squared. Again, separate them out. Left hand side now we have inverse sine or minus inverse cos, whichever you prefer. I've gone with inverse sine, and y then becomes the sine of x plus c. So we've seen those sorts of types already, really. But now we're going to look at this thing called the logistic equation. Here it is. Whoop. It looks something like this. The derivative of function x with respect to x is equal to function x outside of 1 minus function x. Okay. Well, in this course we simplify it down a bit, and really the ones we will see will be in this sort of form. So dy dx will equal some constant times y, p minus y. So they're the sorts of ones we'll look at for the logistic equation. Let's look at it in a bit of detail then. To make life a little bit easier for ourselves, I've made k equal to 1 here. That's just y outside of 1 minus y. I've got an initial condition of when x is 0, y is a. So some number. Now the first thing I'm going to do is I'm going to look at the slope field. So the slope field of this ends up looking like this. And I've drawn in 3 different possibilities depending on what the value of a would be. So if a was greater than 1, because remember a is basically the y-intercept. So if a is bigger than 1, then it would be this blue curve, something like that. If it was in between 0 and 1, I get this inflecting shape. And if it's less than 1, I get the orange one I've drawn in here. Well, an example of that. Now how do I know that? Because in my slope field I ended up with some horizontal lines at the x-axis, but also at y equals 1. So that means they're trivial solutions. So there's actually 5 different solutions we could have to the logistic equation, depending on what a happens to be. Well, let's actually go and find those equations then. So y, 1 minus y. As I say, we know we've got 2 trivial solutions. Remember we said if it is possible for one of those functions to equal 0, then we couldn't separate the variables because you can't divide by 0. So y equals 0 would make that equal to 0, and y equals 1 would make that equal to 0. So there's those 2 horizontal lines we saw in the slope field. Separate out the variables to y on y 1 minus y. We could use partial fractions to do this. And on the right hand side, well, integral of dx is just x. We've got now a couple of log functions. I would have the log of y minus the log of 1 minus y. I've combined that all into one thing there using my log laws. So log of y on 1 minus y. Substitute in the y and the a, and we get the log of y on 1 minus a over a 1 minus y. That's what x is. We're trying to get y the subject. So exponentialize e to the power of x will be y 1 minus a on a 1 minus y. What I'm now doing is I'm saying, well, a e to the power of x then is equal to y on 1 minus y. You see, 1 minus a on a is just a constant number. And so I'm saying, I'm going to divide both sides by that constant. It's still just some constant times e to the power of x I would get. In fact, my constant technically is a on 1 minus a, or the absolute value of it would be a on 1 minus a. But it's still, I know it's some constant times e to the x. Now, playing around with that, because remember we're trying to get y the subject here, a e to the x 1 minus y is equal to y. I eventually get y equals a e to the x over 1 plus a e to the x. Okay, there's a solution. Sometimes you'll see it written like this though. Instead of being to a positive power, it's to a negative power. So all they've essentially done is divided each term by e to the power of x. But to make it a little bit nicer, they also made this 1. So technically we're saying, well, b is equal to 1 over a. It's still the same thing. It's just a different constant they've used there. So you could get it into the form of 1 over b e to the minus x plus 1. Now you might see it written the top way, you might see it written the bottom way, but they're the solutions we could have. So basically, 3 solutions. Y equals 1 on b e to the minus x plus 1, and the 2 trivial solutions. Now, remember I said, oh, hang on, there were 5? Well, b would be different values depending on what a is. Because remember, b is 1 on a, and a is little a on 1 minus a, so it tracks back to whatever a happens to be. Find any inflection points on the curve. Well, we know possible inflection points will occur when the second derivative is equal to 0. So we have to differentiate that first derivative. In other words, we have to differentiate y 1 minus y, but not with respect to y, with respect to x. Well, I can't do it with respect to x, so I'll do it with respect to y, but then multiply by the y dx. Well, differentiate y 1 minus y with respect to y. Write down the first, diff the second, so I've got negative y, plus write down the second, diff the first, 1 minus y, but that's going to be times the y dx, which we said was y 1 minus y. Eventually I get y outside of 1 minus 2y, outside of 1 minus y. 3 possibilities. Actually, only one of them is a possibility. So we're trying to find the inflection point, but we know y equals 0 and y equals 1, they were the 2 trivial solutions. The horizontal line. There is no inflection point on a horizontal line. Therefore, the inflection point must be the one where y is equal to a half. That's the only possibility we have. And we know there is an inflection point, because if we go back to our slope field, we know that in between these 2 trivial solutions, we change concavity. So there certainly is an inflection point, but we're saying there's only one possibility for it, because the other 2 were the trivial ones. So it must be when y is equal to a half. Well, what's the x value then? Because we've got to find the point. Remember, b, some constant times e to the minus x is equal to 1. Playing around with that, I end up with the log of b, but b was 1 minus a over a. There it is. I don't need to test either side, because I can use that slope field. Remember how I said it's like visual integration? So I can use it to my benefit to say, well, look, I don't have to prove there's a change in concavity. You've given me a slope field. We can see there's a change in concavity from the slope field. And so thus, that is our point of inflection. 13D.